Hello and welcome back. Let's close off our calculus journey till differential equations, which I guess you could consider its own thing or you could consider it calculus. It's up to you. But let's close it off with Gauss's theorem, otherwise known as Gauss's law or the divergence theorem. And what this tells us is that if we have a closed surface integral, which you may remember what a closed line integral looks like, this might seem very similar to you, will equal the divergence of our field, all integrated with respect to volume. And so you may recognize that since we have a closed surface, we will now have a triple integral. And this looks very similar to Green's theorem, where if we had a integral over c of p dx plus q dy, we could evaluate it in a double integral of, I believe it's del q with respect to x minus, or not del, the partial derivative with respect to y dA. I believe that's Green's theorem. I could be wrong, but yeah, so it looks like a higher dimensional Green's theorem. Sort of. Although technically I do believe Stokes' theorem is called the higher dimensional Green's theorem. Anyways, let's hop into it. So if we have some type of surface, let's say a little cube here. Whoa. This cube is closed, like that cube right there. We can just integrate with respect to volume and take the divergence of that vector field, of course. So let's look at an example. We have, let's calculate this, where F, our vector field, is x squared plus, or not plus, x squared, y squared, and z squared. Boom. And our surface is the cube I just drew, where it spans from 0 to 1 on the x, y, and z axis. So, how would we evaluate this? Well, we could evaluate all 6 sides of the cube in a surface integral. But why would we do that when we can just do this? Let's take the divergence of this vector field. This is going to be 2x plus 2y plus 2z. Very simple. Now what can we do? Well, we can plug them into this, and we know that x, y, and z span from 0 to 1, so that makes this volume integral very simple. Or, well, sorry, I guess it's not exactly a volume integral, but this triple integral. It's just 3 integrals from 0 to 1 of our divergence of this vector field. dx, dy, dz. And so we can tell here that by integrating this, we could, of course, split these up into their own little terms, and each one would give us 1 when we integrate along their respective variables. And so what we're going to get here is 3. And so that's the divergence theorem, otherwise known as Gauss's theorem or Gauss's law. And yeah, congratulations, because you are now done Calculus 3 if you've watched this entire playlist. Now I would like to just talk about how knowledgeable we truly are now. Well, if you are a physics or engineering student, or just someone that is curious about, say, electrodynamics, I believe it is, not statics, we can talk about these equations now using our vector calculus knowledge. So these are called Maxwell's equations, and they tell us things about electromagnetic fields. And the first one is very simple. This would be volumetric charge density. This would be epsilon naught, the permittivity of electricity in free space. This is our electric field, but we can actually apply Gauss's theorem to this exact problem. And so what it will give us is something that we don't use a lot, but something that is the basis of a lot of physics and problems like that in sciences. And so, of course, if we took the integral over here, we would get this, and so then we can change it into this. Another one of Maxwell's equations would be the curl of an electric field is equal to the negative partial derivative of a magnetic field with respect to time. And that's a very interesting one because it tells us that, say we have a closed circuit of electric field, or otherwise known as current. This would be a rotating electric field, and that can be produced by moving a magnet in and out of this. And so that is why there's a negative to account for that. The next one would be del dot B equals 0. And all this tells us, and I think I talked about this in an earlier episode, is that the divergence of any magnetic field is 0. And this would be very simple to do this on. This would tell us that the triple integral over E of del dot B dV still equals 0, and that would also equal the closed surface integral of B with respect to, I believe we use area in physics, although it's the same thing. It's not a capital A because we know respect to area just gives us 2 dimensions. Now there is one very complicated one that also relates electric and magnetic fields, and that would be del cross, the curl of our magnetic field is equal to mu naught J vector plus mu naught epsilon naught times the partial derivative of our electric field with respect to time. And now, to be honest, I have absolutely no clue what this equation tells us, although it is also transferred into integral form using, not this, it would be Stokes' theorem since it's a curl. But thank you very much for watching this series. I hope it has helped you as much as you needed, and I hope to see you in whatever series I decide I am making next. To be honest, I don't even have a clue. Thank you.